So I'm eating this bag of like chips, and it's like flavored fried pickles and ranch. Not gonna lie, it's not bad. It's from Lay's, by the way. If you guys want some, I don't know, order it. Or buy it from like Sam's Club or something. Sam's Club has like this piece of steak. You can get like 30 pieces of steak out of it for $120. But let's talk about vector equations of lines and if they intersect or not. This is the first problem we're going to do. I'm going to show you how you can solve for intersecting lines using these vectors equations, or maybe even different formats of how you can represent lines in 3D using vectors. So I'll start it off by saying that t right here for this line, I guess you could think of it as time, but not necessarily. Just think of it as a scalar value that allows this vector right here to get longer or shorter. Longer or shorter. Same for s. S is not t. S is basically the t value, but just for this vector only. They're a little bit different, but bear with me. But when we have a vector in this format, let's change it. Okay, let's change it to something that maybe would be easier to, I don't know, understand. So this vector here is also equal to 1 plus 2t and 2 minus t and 3 plus t. And how I got that was by distributing t along every single thing here. So 2t, negative t, and just t. And I added it onto each individual number here, just like adding normal vectors, right? So we have a vector 1, 2 plus like 2t minus 3t. You can add these vectors still to get 1. I didn't mean to put that dot down. 1 plus 2t and 2 minus 3t. So you can still add these vectors like normal, and that's what we did here. We just distributed the t along every single value inside of this vector, and then we combined it together by adding the two vectors, these two vectors right here. I don't know why I write slanted with this pen. Okay, let's go on. Now we can distribute the s along everything here. So we have 4 plus, not plus, 4 minus s, comma, 1 plus 2s, and since it's 0, we just do nothing, and we get 3s only. There is no scalar value like this. Like this. We'll just have 3s over here. So, what can we do with these? Well, now that we have these equations, what do these actually represent? Well, this represents I hat, and this represents the I hat value, or we can say just x, y, z values, x, y, z values. And we can actually just assume they're equal to each other. So, right now, I'm only determining if these lines intersect or not, and if they do intersect, I will show you how to find the point. But let's actually just assume for a quick second that these lines do intersect. And in that assumption, we can actually set up a system of equations. So if we assume x is equal to, these two x values are equal at some point, that means there is some point in s and some point in t where both of these equations hold true, meaning that we can set them equal to each other. Same for the y values. Minus t. 1 plus 2s, 3 plus t, and 3s. Now, once we set each corresponding x and y value equal to each other using their vector equation form, we can solve for one of the systems, because all these t's must be the same, all the s's must be the same in order for the lines to intersect at some point, and for all the equations hold true as well, we can honestly just ignore, let's ignore this guy over here. Let's move him somewhere else for now. And we could just solve for this system right over here. So how do you solve for this system? Well, let's move all the values of t and s onto one side. And this is also equal to 2t plus s is equal to 3. And this is negative t minus 2s is equal to negative 1. And honestly, we could change everything to positive here. So t minus 2s equals 1. I mean t plus 2s is equal to 1. I think that should work. Yeah. So now we could solve for this, right? Using elimination or substitution, whatever method that you're comfortable with. I think this problem will be easier to use substitution. So what we can actually do, we can turn this form right over here into I don't know, t is equal to 1 minus 2s. And we can actually substitute this t back into this equation. So what do we get when we do that? We get 1 minus s plus s is equal to 3. Now we can just solve for s here. So distribute the 2 along each value inside of these parentheses, plus s. This is what we get is equal to 3. And we just simplify the rest of this, and we get 2 minus 3s is equal to 3. Let's keep going. Equal to 1, and s is equal to negative 1/3. Now that we have s is equal to 1/3, we have to substitute s back into here, and we need to find some value for t. So let's substitute s into here. So let's do it in the other equation actually. T plus 2 times negative 1. What? My pen's messing up. 2 times negative 1/3 is equal to 1. We get t plus, or t minus 2 over 3 is equal to 1. And that means t is equal to 5 over 3. Let's keep going. Let's substitute s into this equation up here, and the t that we solve for this equation up into here to see if it's right. 2 times 5 over 3. Dude, really? Two times 5 over 3. 2 times 5 over 3 plus, or technically minus 1/3. Then what do we get? We get 10 over 3 minus 1/3, which is equal to 9 over 3, which is 3. So these values are right for these two equations. But do they hold true for this equation down here? The z values still matter. Even if the x and y values are the same for these intersecting lines, are the z values the same? Well, we have to solve for that. And all we can do to solve for that is just plugging in whatever values we got here. So 3 plus t, which is 5 over 3, is equal to 3 times negative 1 over 3. Right? And once we solve for this, go 3 plus 5 over 3. 5 over 3 is equal to negative 1. Is that true? It's not. So these lines do not intersect. They're likely skew, which means that they aren't parallel, but they just never intersect at any point. Now, what did we do here? I'm going to do a quick recap on what we did. And I ordered the steps 1, 2, 3, 4 for you guys so it's easier to follow. But what we did, turn this equation form, okay, really bad underline, turn this equation form into something that looks more like this. we created a system of equations around this area, so we can solve for t and s, but we only used two of the functions. So this is the x value, this is the y value, and this is z value. We actually, remember, we moved the z value down because we'll just save it for later. And this x value and y value for each function, 1 plus 2t, is an x value for the t function, and 4 minus s is an x value for the s function. And we assumed that they were equal to each other, okay? So we set them equal to each other at some point. They must be equal to each other at some point. We also did that for t over here, t and s, with the y values. Now we ignore the z because it's easier to solve two systems of equations or two equations rather than three. So we solve for t and s along with step 4 and 5, and we found that s was negative 1 over 3 and t was 5 over 3. Now, at these points in time or whatever values you're talking about, x and y are equal to each other. X and y values are equal to each other. Does that mean the z values are equal to each other? Well, we plugged in. We actually went up this time instead of down. Sorry, I should go in a order, left to right, up to down. But we plugged in the s values and t values that we found, where x and y were the same, and then we plugged them into the z value to see if the z values are the same as well. If the z values are the same as well, then that means the lines intersect at those given s and t values. So we plugged it in. Are these equal to each other? No, they're not. Therefore, these lines do not intersect. Now, let's move on to the next problem. This next problem, let's hope the lines intersect this time. I'm not going to lie, while I'm doing these, all I did was search up the practice problems, and I don't know the answers to them. So I'm solving them along with you. But let's start it off by turning these equations into the ones that are easier to see the components of each. So this one turns into 1 plus 2t, and this one turns into 2 minus t, and this one turns into 3 plus t. This equation down here for s turns into 3 minus s, 1 plus 3s, and 4 minus 2s. And let me double check that real quick to see if that's right. 3 minus s, 1 plus 3s, 4 minus 2s, 1 plus 2t, 2 minus t, and 3 plus t. Okay, these make sense. And remember how I solved these? How I solved for these equations was by distributing t into here, to each value of this vector, and then just adding the vectors like normal. And then we got these. So first thing we did, we're going to assume that these two are equal by creating a system of equations. This is the x value for the t function, and this is the x value for the s function. This is the t value for the the y value for the t function, and this is the y value for the s function. Let's mark them off again. And remember, we have the z1, but let's just ignore it. Let's leave it on the bottom. Sorry, z. Okay. Let's keep going. Let's solve for this. So, how do you solve for this systems of equation here? Well, we're going to set it equal to something else. 2t plus s is equal to 2. Sorry, I didn't write the plus for some reason. Plus s is equal to 2. And this one is equal to 3s plus t is equal to 1. Okay. Let's keep going on with this. I think I'll use elimination this time. You know what? Let's use substitution again. So let's substitute. Let's substitute this bottom one. Let's turn this bottom one into something that can be substituted into. So t is equal to 1 minus 3s. Correct? So that means we could substitute t into here. So we can substitute this into this t right over here. Let's put t into this. So this turns out to equal 2, 1 minus 3s plus s is equal to 2. Now we just have to solve for s because there's just one variable here. Distribute the 2 plus s is equal to 2, and then 2 minus 5s is equal to 2. Therefore, minus 5s is equal to 0. So s is equal to 0 here. So now that we solve for s, we can just solve for t. Well, we can just plug in 0 into this equation here. So 3, 0 plus t is equal to 1. Therefore, t is equal to 1. So we solve for s and t for the x and y values. So at these s and t values, x and y are the same. Okay, you can plug it in yourself and figure that out. If we plug in s into 0 over here, this is equal to 3. If we plug in t into 1 here, this is also equal to 3. Oops, 3. And if you plug in 1 into t here, this is 2 minus 1 is equal to 1. So this is equal to 1. And s is 0 here, also equal to 1. 1 plus 0 is still 1. So at these s and t values, x and y's, the x and y values for these lines are the same. Does that mean they're the same for the z values, though? Well, we can find that out by plugging in s and the t values into this. So let's plug in s and the t values into this. Let's put 3 plus, what's t? 1 is equal to 4 minus 3 times 0. And this turns out to be 4 is equal to 4. So therefore, at s0 and t1, these lines intersect. The z values are the same, and the x and y values are the same. Therefore, it's the same point in which they intersect. Now, let's just solve for the point that they intersect at. Oops. Let's move this somewhere else. Move it up here. Let's solve for the point that they intersect at. So we just got to plug in 0 and 1 into any of these two equations. So let's plug in 1 into here. So 1 into the t function is equal to 1 plus t, 2t, which is just 2. 2 minus t, which is just 2 minus 1. And 3 plus t, which is equal to just 3 plus 1. So at this coordinate point, and let's actually just remove the vector symbols because this is not actually a vector. At these coordinate points, these vectors are at this coordinate point. These two lines intersect. Now, let's determine if these two lines intersect. Well, these two lines, let's start off with turning them into the equations forms. So we can do 1 plus 3t, comma, 0, which is just, this is just t. 0 plus 1t is just t. And 2 plus 4t. This is equal to 4 plus 6s, 1 plus 2s, and 7 plus 8s. Okay, I'm going to label the corresponding coordinate representations for each of these functions. And let's just set, again, assume x and y are the same. So we set them equal to each other. Sorry, this is 4. It's supposed to be 4 plus 6s. And t is equal to 1 plus 2s. And let's leave the z function all the way at the bottom alone, like you guys. Here, let's solve for this. Well, what do these functions equal? So we have 3t minus 6s is equal to 3. And let's just leave the bottom the same because we can just substitute, actually, the t into this up here. So let's solve for the system. Substitute t into here, and then we get, let's sub over here. Let's actually use a different color so it's easier to recognize. So substitution, and we substitute t into the function above, so we get 1 plus 2s minus 6s is equal to 3. Let's actually make, now I'm going to make this smaller because I'm going to run out of space. 3 minus 1 plus 2s minus 6s is equal to 3. So distribute the 3 along each of these values inside the parentheses. And what? 3 is equal to 3. The reason why we see 3 is equal to 3 here is because these functions are equal to each other. They are the same exact function. Let me show you why. That's right, 3t minus 6s. And I can tell you what you can come up off of that conclusion. So we're going to isolate the t and the s values onto one side. Let's go t minus 2s is equal to 1. Does this look familiar? What do you see here? Well, if you multiply 3 into every single one of these values here, then 3t minus 6s is equal to 3. See, these two functions are just the same things, even though they represent different values. And what does that mean? That means that, let's actually show you. Let's extract the vectors out of this. So these are the two vectors here. What went on there? These are the two vectors here. Let's extract the vectors that are parallel to the lines. So this is the thing. These are the vectors that represent the line. Basically, they show you which direction the line goes in from this point here. And I actually explained this inside of my introduction to lines in 3D video. So we're going to extract these two values. We're actually going to get 3, 1, and 4, and 6, 2, 8. And these are the two vectors. This is for t, and this is for s. These are two vectors that determine which direction each of these lines are going from their given points. So notice how these 2 points are different, but the vectors are actually parallel to each other. So if we multiply this t vector by 2, we get 6, 2, and 8. And both of these vectors are the same. They're parallel because they are scalar multiples of each other. And what a scalar multiple is, if you don't know or if your teacher didn't cover it, a scalar multiple of a vector is basically when you can multiply a number like 2 into a vector and just get the same thing as another vector. Therefore, these two are scalar multiples. It would be the same if this was 9, 6, and like, if this was 9, what was it? 9, 3, yeah, 9, 3, and 12. Because if you multiply this by 3, these would come out to be 9, 3, and 12. So scalar multiples of vectors just mean that they are equal to each other if you can multiply any scalar value by either one of them to get the same thing. Therefore, since these two vectors are parallel to each other, so these two vectors are the exact same things, basically, just with different magnitudes, and these lines start off on different points given by the first part of the function, these lines are parallel. Therefore, they do not intersect. If lines are parallel, you already learned this in early algebra too. If lines are parallel, they never intersect, ever. So for the last problem, I'm going to give you a different form of which you might be able to see some of these vectors equations of lines intersecting, or any problem that you get. I'm just going to show you a different form. So don't worry, this form is actually easier because these x values, again, we'll just assume that they're equal to each other. So this is just another way that you can represent a line in 3D space. But let's set these x values equal to each other. So let's do 1 plus 2t is equal to 4 minus s. We're assuming they're equal to each other, and we're solving for the x and y values first. Ignore the z values for now. 3 minus t is equal to 1 plus 2s. So let's solve for the system. Let's actually isolate them first. Let's isolate the variables onto one side. 2t plus s is equal to 3, and 2s plus t is equal to 2. Now, after finding this function right here with the x and y values, what we do, again, we use some form of method to solve for systems of equations. So this will be either elimination or substitution, and I'll use elimination for this one. So when using elimination, let's multiply each of these values by 2. So then we get a new function like, 2t plus s is equal to 3, and we multiply everything over here by 2. My mouse pad is like sideways right now, by 2 to get 2t plus 4s is equal to 4. And let's subtract both of these equations. And then we can get, dude, why is my writing slanted? Let's try my best to make it straight. And once we subtract, these two cancel. S minus 4s is equal to negative 3s, and 3 minus 4 is equal to negative 1. So s is equal to 1 over 3. What just happened? S equal to 1 over 3. Now that we found s, let's plug in s to, I don't know, let's choose this function right here. So 2t plus 1 over 3 is equal to 3. So what does t have to equal for this to work? Let's continue making this simpler. And this is what? This is 10 over 3. Nope, sorry. 8 over 3. Therefore, t is equal to, I don't know, what is this? 4 over 3, yeah. So now that we found the values for s and t, all we have to do is plug in the s and t values for z as well. Because this system of equations solves for the s and t values where x and y are the same. X and y are the same. But that doesn't mean the z values are the same. So let's plug in s and t. So let's use this one first. So 2 plus 3t is equal to 4 over 3, which is equal to 3 times 4 over 3 is 4. 4 plus 2 is 6. And then let's plug it in for this equation now. S minus 1, and s is 1 over 3. Minus 1 is equal to, well, obviously, from what you can tell now, these are not the same. So 6 and negative 2 over 3 are not the same. So therefore, since these lines have a point in which x and y are the same, but the z values are not the same, this line is skew. If you have any questions, put it down in the comment section. This was a video explaining on how to solve the for the point where two lines in 3 dimensions are intersecting. First thing we did, a little quick recap, was solve for a system of equations with the x and y values first. Assume that the x and y values are equal to each other, and then once we set them equal to each other, we got equations like this. We created a system of equations, and these system of equations we solved for s and t here. And these values of s and t are the values where x and y are equal. The x and y values of both of these vector equations for lines are equal. But that doesn't mean the values of their z values are equal. Therefore, we just plugged in s and t values for the z value to see if they're equal. And if they were equal, then the lines intersect. If these values turned out not to be equal, like this case here, then the lines are skew. And another method that we used was seeing if lines are parallel. So if you have the vector equation of the line, or you have the vector that is parallel to the line in the format x null, y null, and z null, plus t of some vector a, b, c. This vector here is the vector that is parallel to the line, and this is the one that controls which direction the line goes to compared to this point. And if the two equations have vectors that are scalar multiples of each other, the vector equation lines are parallel.